No, only if you don't have one of these.
Okay.
How's it back?
Right, can everyone hear me all right? No. Okay, obviously you can. So, yeah. It's a fractal we're sort of zooming into at the moment. It's got the sort of level of magnification up here. So we're sort of you know, to the power of 9, 10 zoom. If you look at the sort of the scale scales of things, the smallest possible thing is Planck length, which is about 10 to the minus 35 meters, and the largest thing in the universe is the universe itself, which is about 10 to the 35 meters. That gives a scale of, you know, smallest to largest about 10 to the power of 70. Now, if I zoom along here somewhere, so there's 10 to the power of 70 there. Basically, if we were to draw that entire fractal at that scale, at the sort of 10 to the power of 70, it would be bigger than the entire universe. So the level of zoom on this is quite phenomenal. This is a part of the Mandelbrot set, which we're talking about very shortly. So, just a little bit of history first off. So, in 1977, the Cray 1 was released. It was sort of the first supercomputer, and you could actually buy one. So, it wasn't one of a kind. It would cost you $8 million. That's probably about 150 million in today's dollars. So, not overly cheap. Weighed 5.5 tons. Operated at 80 megahertz, and could, it was free on cool. Basically, you know, it's not like the liquid cooling with computers today, which is just a little pump that pumps water around. This is actually immersed in Freon. So basically, because they wanted to minimize latency, all the boards were just basically sandwiched together really, really close. So it basically required liquid cooling. Air cooling wasn't an option. And so it could do 0.16 gigaflops or billion floating point operations per second, so 160 million floating point operations per second.
And it seats 12.
Yeah, looks like it, doesn't it? So, okay, skip forward from 1977 to 85. We've got the Cray 2. You can buy one of these for 16 million. So probably similar price, sort of inflation adjusted. They've got a fancier cooling liquid, so using fluorinert. It's a 3M product. Had 2 gig of RAM and could do 1.5 gigaflops, so 1.5 billion floating point operations per second. Okay, forward to 1990. So we're going ahead in about 5-year intervals. So $25 million. Okay, 22 gigaflops. Numbers are getting bigger. So Japan sort of led the supercomputer race for quite a while, and then sort of the US, and now it's China. So forward to 96, 2048 cores, 368 gigaflops. It's getting pretty fast, but now we're going into teraflops. So 2002, over 5,000 cores, 3 terabytes of RAM, $500 million to build this machine. So if you 36 teraflops, remember that number. So now we're into sort of when IBM was building the world's fastest computers in 2007. Big Blue. So one of these, I don't think it was this one, but one of the things beat Gary Kasparov at chess. It's the first time that a supercomputer could actually beat one of the grandmasters. And they're actually now beating grandmasters and people that play Go, which was infinitely more complicated, infinitely orders of magnitude more complicated. But anyway, so basically each one of these boxes, these are basically racks of motherboards which contain CPUs, 130,000 of them. So basically to get faster these days, you have to build bigger and bigger and more cores. So 2011, back to Japan. So we're 88,000 core CPUs with 8 cores each. $1.25 billion 10 petaflops. So we've gone from giga, which is billion, teratrillion, peta.
10 to the 9.
Anyway, it's huge. The numbers are ridiculously large. And the current running champion, the Sunway Tahoe Light, or Tahoe Light, I'm not sure how it's pronounced, but it's got 10 million cores. So this is this is quite a bit more substantial than your average desktop. And the other interesting thing about this is it's all Chinese made. So America said, no, you can't have any fast CPUs. So China will turn around and build their own. But it's 93 petaflops. The new one is going online shortly. I think it's 103 petaflops. It's also Chinese. So,
but they reduced the price.
I don't know. I don't know how much the new one costs. So to put that in perspective, my first computer that my family owned was an 8 MHz 286. It had no math code processor in it, so 0 gigaflops, 0 flops. In fact, if you could probably emulate it down. I don't know. You might get a few 100,000 floating point operations per second. I don't know. But the first computer I bought was a 4860 X250, 0.05 gigaflops. So kind of on the same order of magnitude as the Cray one, which was 0.16. So this is 1/3 the speed. My current home PC is an i7. The CPU in that does 177 gigaflops. So it's pretty fast. But what's interesting is my phone, the CPU will do 3 gigaflops, but also has a GPU on it, so the graphics processing unit, which is basically designed to do single position floating point operations really, really fast, 172 gigaflops. And graphics card, my current graphics card is 3 teraflops, but you can go to a store and buy a GTX 1080 graphics card, NVIDIA. It'll do 9 teraflops. You probably have clock it to 10, and I think that they've got a new Titan out, which I think does 11. You can buy 4 of these, put them on a computer with a suitable motherboard. That gives you 36 teraflops, and if we go back to that one, the NEC Earth Simulator, that's 36 teraflops as well. So that costs $500 million. You can now go to a store and buy a machine, same computational power, for under $10,000. So, so it's this sort of 2002 era. My phone would be the sort of fastest computer in the world in about 1985 or so, somewhere around there. So what you have at your disposal is a phenomenal amount of computational power. So what are we going to do with all this? Play Pokemon Go. So yeah, this is similar in speed to the Cray 2 supercomputer, just with the CPU wise. So it's at 1985. And yeah, you can't play Pokemon on a Cray 2. So I know what I'd rather have. So we're going to be looking at the Mandelbrot set today. Now, just a little bit about it. So it's on a complex plane. So many of you will be familiar with complex numbers. So they have a real part and an imaginary part, and we can graph that on the real part on the x-axis and imaginary on the y-axis. And we divide that plane up into pixels, and with each pixel we'll have a coordinate, and we use this formula on the coordinate, and we iterate it a number of times until either there are 2 conditions. The first is we reach a bailout value, so it exceeds a certain value. So the bigger value, I think I've picked 64, but it's somewhat arbitrary. It needs to be I think a bit larger than about 4 or so. And the other is a maximum number of iterations, because in this black area it requires an infinite number of iterations to, that is to say, you never get out of this black area. Every time you iterate this formula, it bounces to a new location within the Mandelbrot set. And basically, we colour the pixels based on the number of iterations. So we'll make one iteration blue, next one 2 iterations red, and so on. Okay, so let's look at the code. I'll just go back to that slide. So I'm going to create a new multi-device application, and we're just going to build a really sort of rudimentary user interface. So first I'm going to throw on a multi-view and make that a reasonable size. Call it MV settings, and I'm going to throw a button at the top of that. Oops. Line to top. And we'll throw some margins in there so it's a little bit. Oops. Hassle with the mouse being on a inclined surface, it tends to drift. A little bigger. And give it a name. Name property. Calculate. Oops. Okay. Yeah. Okay. And I'm just going to throw one more button. And I'm going to remember to anchor it to the top right hand corner this time. Right. And it might be lazy not call it anything, but on my master view, there's a master button, multi-view rather. It's button 1 and on button 1. We'll make the style look like the little sort of hamburger menu details. Okay, and we want something to draw a fractal, so I'm just going to throw on an image, and I will call it MultiDevice manual and the line client. And the camera can't click on the button, I need to send this to back. So that's our reasonably rudimentary user interface. I do need to make one more adjustment because I want it actually to be disappear completely. And to do that in the on create. So navigation options and collapse width. Now, is that text readable? So don't use it. We need to make that bigger. A little bit bigger. Try and get the keystroke.
Picture's blurry.
No. Function control. There we go. Try that a bit. Okay. So that's basically our user interface. We now want to write our fractal. We'll write our code to generate fractal. So we need a Mandelbrot. We need some sort of thing for our complex numbers. It's our imaginary and real components of it. And they need to be floating point numbers, so we'll use doubles. And there's a bunch of operations we want to perform. So we need to be able to square it. We need to be able to add another complex number to it. And I'm going to call it was absolute value. I started that, I got told off in the last presentation because it technically wasn't absolute square. because taking the square root is a slow operation and would avoid it. So the absolute value of a complex number is basically its distance from the origin. So basically we're forming a right angled triangle, and we want to know the diagonal, so we're squaring the real and imaginary parts and adding together the sum of the squares. So result is times r plus I times I. Technically we want the square root of it, but square roots are, we'll compare it to the square of the number, so we're comparing squares rather than comparing the square roots, so that's basically the same, but faster. Adding is rather trivial. So new real value is the original value plus C dot R, and the page up and page down keys are right beside the cursor keys on this keyboard. It's a bit frustrating. So that's adding our two complex numbers together. Squaring is a little bit more complicated. So R gets R squared minus I squared. But I need to know the R value, the old value. So just keep a copy of our original R, and our new I value is 2 times 0 plus, times I. So if you're familiar with complex numbers, it's fairly straightforward, but you actually don't need to know. So but that's the formula for squaring a complex number, effectively. Now, we need somewhere to store our fractal data when we calculate it. So we have a T-Mendel data, which is an array of integer. And then T. The actual, we're actually going to do form the calculations and what have you. We're going to class and have predicted and public. So we're going to store our data in our array. I need a constructor. Which has a width and height, both integers. Integer, not plural.
Should Mendel data be an array of complex numbers rather than?
No, so we are calculating the number of, we're going to store the number of iterations required to, so it's an integer. Typically we could use like a word or something like that because we don't actually need a negative value, but we're not going to be calculating past 2 billion iterations, so because we'll be here all, for eternity, I think, probably till the end of the universe, but and I need to store those values. I actually don't need to store them technically speaking, but it saves a bit of typing if I do. So some rather boilerplate stuff. Now, we need to define our array. So we're going to set data to be an array of width arrays of height of integers. Now, there are some other properties that we're going to need. They are the maximum number of iterations that we can bother doing, and the bailout value. And they can both be integers. And need to define the top left-hand corner, if we go to our picture, our top left-hand corner, and our bottom right-hand corner of our sort of plane, or our viewport on the plane. So I'm going to make the maximum iterations be 1024, because it's a round number, I suppose. Bailout value is 64. I think anything above 16 is probably a safe value. So, in fact, I'll just copy these from the last. Create. So our left-hand side is minus 2.5 up to 1.5 high, and down to 1 on the side, and down to minus 1.5, which should include the entire fractal. So that's our constructor and all the sort of data points we need. What we want to do now is to calculate our fractal. Now, basically we need to iterate over every pixel and perform some calculation. So for y to assign 0 to height minus 1, do x minus 1, and we want to set the value in our array to be something. Which we will define now. So the calculate pixel can predict it. That's right. Okay, so this gets a little bit more complicated, but what we're going to need is Z and C, which are both complex numbers. So this is our Z value, and C is the initial, is defined as a constant. It's our initial value, and we need to determine those somehow. So C is quite simple. It's going to get whatever Z is, and Z. So we've got a pixel, a location, and we want to convert that to a complex coordinate. So writing it. Now, I'm not going to actually bother writing this one. I'm actually going to copy and paste it. In fact, there it is there. So, this is not particularly exciting. Let's kill that one. Gives it more room. So basically we're just translating coordinates. So it's not, so we're just converting integers to complex numbers. And there should have been a function which returns an integer. And if I go Control-Alt-Shift-P, that will automatically update the definition as well. So, a shortcut key, if you're not familiar with that, that was introduced as part of the Castalia, which is integrated with Delphi a couple of versions ago. So, we now need to do a loop whereby we want to stay. Oops. We've got two conditions. The first is that we haven't exceeded our maximum number of iterations. So start at 1, and while result is less than nice if that were completed, but and also the z dot absolute square is less than our beta 8. Now we got there on the right way.
I think it was greater than yesterday.
Yeah.
So there's some crash.
So y is it and well no so y is less than the absolute square, we want to carry on. So into our result. And so the formula, z is assigned z squared, and c. And that's pretty much it. Not a hugely complicated mathematical expression, but the one thing I'm going to do, if result equals the maximum number of iterations, I'm going to make result 0, because it's going to be the inside of our fractal, the black area. Okay, so we've written a bit over 100 lines of code, probably remove some spaces and get it to be 100 lines. And this is basically, we have enough code there to generate a fractal. Now, we want to use that, and we will want and of course we'll need to create it. Okay, and define the width and height of it. So now in FireMonkey, the coordinates are all in single point, they're all singles, so floating point numbers. So this it's a good thing, it's the only error. We need to round, or at least in some way convert them to integers. Okay, and I suppose if we are being correct about things, we should also free it. Now I'm going to write two procedures. Draw fractal. And calculate and draw. So calculate and draw, that's fairly straightforward. Manual dot calculate, and then to draw it, draw fractal. Now, draw fractal is a bit annoying, so I'm just going to copy and paste the code I wrote yesterday. actually, of course, I didn't write yesterday. I copied it and pasted it from code I wrote previously. So, and I'm just going to comment out that for now. So, what we're doing here. So, if I was being more efficient about this, I'd be painting directly onto the form canvas and doing that. But I'm a bit lazy, so I'm just drawing on a bitmap within a T image. Which is probably far from efficient, but suits our purposes quite nicely today. So I'm just grabbing the width and height of Mandelbrot and then making sure that the image is that size. So I'm just grabbing the bitmap from the Mandel image. And then we have to do this map procedure to be able to gain access to its internals. And in the internals is this T bitmap data, which we can then draw on. And of course, in the end, we have to unmap it as well so that things get updated. Now, all we need to do now is decide on what colour we want to draw our fractal with. So, if Mendel dot data equals 0. So 0 is the inside of our fractal. T alpha color rec black. Okay, if it's not on the inside of it, we are going to make it white. Now I didn't get this working first time yesterday. Let's see how my black is today. Of course it's not going to work because I'm actually calling calculator draw yet. So calculator draw. Okay, first time. So, I think about one. I've rehearsed this heaps of times. And about 1/3 of the times I do it, I get it to come out right. So, so that looks very similar to our example fractal here. But it's not as pretty as these ones. So we want to have some nice colours on our fractal. We could write, if it equals 1, then this colour, if it equals 2, 3, and so on. That would be quite painful. So I am again going to cheat, because that's the fastest way of programming. That's the one I want, and it's that one and that one. Okay, so just use those units. But basically, these are a colour map. Effectively, you can think of it as an array of colours. So this is our FireMonkey version. And it has this map, which is a T fractal colour map, and this is a platform agnostic version of it. So this version can work with VCL or whatever. And basically, I'm just initialising it with a whole bunch of values. I've got a load file and stuff like that, but come here and I'll uncomment this and delete that code. So now we just need to define our colour map. There's a TFMX fractal colour map. Creators. And So hopefully now, we actually did something, and actually some slightly stronger contrasting colours, but you can see sort of there's a lighter colour around the outside edge of it, and when we start zooming in, it'll look a lot more colourful. So, what do I do next? So probably we'll quickly implement zooming, because that's quite interesting. But we'll do that by copy and paste again. So we go back to our Mandelbrot class, and find it now. Oh, which one was I doing? Did I compile the wrong one? That'd be slightly silly, wouldn't it? I'm pretty sure I got that right. Okay, I must have just switched to the wrong one. ADUG one. Okay, back to our Mandelbrot set. And I want these three methods. So let's just copy those in. Control-Shift-C. So basically our zoomed pixel just recenters on the pixel that we've selected, and then shrinks out our viewport slightly so that we magnify our fractal. And these are just the kind of awkward things to write. So basically, yeah, just shrinking and recentering. So it's basically, again, a translation of coordinates and things like that. And the other thing I think other thing to do is make recenter on pixel public. So we go into the on mouse down event of our image. Recenter on pixel. Oops, page down again. And can't click that drop. Now again, it's going to fail because we need to do round and we can now zoom in or not zoom in. Interesting. Centering it, so what's going on there? Did I not copy a method? That's probably what's happened. No, that doesn't make sense. So recenter on pixel. Yes, thank you. I wanted zoom to pixel. Okay, hopefully that'll look slightly better. So, and just thinking about it. There we go. So we can now zoom in, and we can see that the Mandelbrot set exhibits this self-similarity, so this looks similar to the original shape, and we can zoom in again, and so on. So before we get too carried away with zooming, we now want to start doing some optimizations, because the code we've written, or I've written so far, is not the fastest we can achieve. But in terms of, to improve, we also need to measure. So if we come back to the Mandelbrot class. System.diagnostics. And in the calculate, let's have a stopwatch. Stopwatch.start new and elapsed milliseconds. And we need to define that somewhere. I suppose we could also have a return the calculation time. But so just want to update our user interface slightly by adding a label, which we will again align to top. Count time. And now, calculate and draw. We'll do gets. Calculation time, milliseconds, toString. Okay, so, oh, another thing. Let's, in the form show, we have to click on the button quite so often. Okay, so that's taking almost 1.6 seconds. That is over 1.6 seconds. So 1.642 seconds approximately is our starting point for our optimizations. So the first thing we can do, if we come back to our class, some of these in T-complex number, these methods are called a lot. And when you call it a function, it sets up a stack and a bunch of other stuff, and there's these, a jump instruction and a jump and return and all that kind of stuff. So if we eliminate all that, we'll save a bit of time. And you can do that by calling inline. So that rather than when Delphi compiles, rather than calling the function, it just copies and pastes effectively the contents of that function to where it's being used. And I suppose that's called a lot. Okay, so what have we gained? So 1.46, 1.54, 1.54, 1.54. So we sort of gained 100 milliseconds of performance improvement by doing that. There is one other thing that actually makes quite a big difference, a large difference, is in that this T-complex number is actually, it's two doubles. A double is 8 bytes, effectively. So we're having to shuffle around an extra. So when we call this function, it makes a copy of our T-complex number, our C, unless we specify const of, but we're not modifying, so const is fine. And also Control Shift P, and that will actually save us a bit of time, because 16 bytes of memory is a lot. It's not actually. When you're shifting it around millions of times, it doesn't make quite a difference. So we're down to 1.272 milliseconds from 1.6. So we've managed to, so this is sort of traditional optimizations, we've managed to knock off about 400 milliseconds, which is, it's not bad. We've got about a quarter of the calculation time, so can't complain too much. But there are some other things we can do. Do you want to throw out what would be a good thing to do? Okay, well, something that came up last time. Let's just bring this back to default layout. Was we're doing this as currently a 32-bit application, and these doubles are 64 bits. So might 64-bit be faster because it can copy that entire value in a single step.
How about release build?
Okay, we can try that as well. So we're down to 540 milliseconds. So, you know, quite often actually 64-bit applications are slower than their 32-bit counterpart because the, you know, pointers are bigger and all that kind of stuff. But in this case, because it's a highly mathematical task we're performing, and it's pretty much, you know, we're just doing lots of number crunching and of 64-bit numbers, it improves a lot. So that more than halved calculation time. So that's a pretty good. Now, release. So rather than clicking on debug, I'll click on the run without debugging, and it actually makes a difference, effectively. Maybe a small difference.
Oh, I was thinking more of the build.
Sorry?
The build configuration.
Oh, move. Okay. So Shift F9 to do a full. Okay, so we've knocked off another 50 milliseconds or something like that. But I'm going to put it back to debugging because in case we want to, because I'm going to want to set a breakpoint at some point. Okay.
What's the cost of the inline declaration?
No.
No cost at all?
Ah, sorry, the executable becomes slightly larger.
Okay.
So it takes up more memory, but considering how long those
no, I
methods
get it.
are.
There must be some trade-off.
Yeah.
Just make everything inline. So.
Yeah, so, yeah, otherwise, yeah, it's the same as you could write your entire application in one procedure. It would make it faster. Perhaps not faster to write, but yeah. So yeah, inlining, but it doesn't always work. There are lots of restrictions on where you can inline and where you can't. I can't remember off the top of my head, but those are instances where it's possible. If I remove fractal color map and I go Shift F9, we get this interesting warning. Get color has not been expanded because fractal color map is not used. So that is basically saying that I've inlined that, and I've probably inlined fractal color map, inlined that. I think it's saying that inlining is not occurring because that's not my uses. But anyway. So when you're porting Delphi applications from older versions, often you get the something about message box, something that's not expanded is one that commonly comes up. You get system dots, something like that. Digressing anyway. So. Okay, so I'll just mention one more thing before we get too carried away. What I'm going to do is start zooming in, and I'll try and zoom in on areas where it's going to be fairly quick. And as you can see, we're actually zooming in quite substantially. And it is starting to get a little bit more slow. And at some point, we're basically going to run out of precision on our floating point numbers.
Mm.
And
Never mind.
oh, there we go. Okay. And you can barely see that. So I've chosen a rather bad area. But basically, we're just big rectangular pixels. So that's sort of where our double precision floating point numbers run out of precision. So if we're doing 32-bit, we could actually use extended floating point numbers, which gives another 2 bytes, 10 bytes. They're not supported on 64-bit, I don't think, at all, because it's slower to calculate with. And no, they're not 64-bit, they're 80 bits. But if we wanted to go significantly further, we have to then write our own floating point arithmetic. So, which becomes really complicated, really fun. It's not fun, but interesting, I suppose. So, so there are limits to what our floating point numbers can achieve. Zooming in. Okay, so we've looked at all the sort of regular optimizations we can do. The next sort of interesting thing we can attempt to do is multi-threaded programming. Has anyone use T-thread quite a bit? Yeah. So T-thread is not the friendliest of things to play with. You can shoot yourself in the foot really quickly, and then you can sort of shoot from some random direction and it bounces around and eventually shoots you in the foot. And you don't know why your program's crashed, but so if I would, that's where's our calculate. So if I wanted to rewrite this using T-thread, it would probably look quite hideous, and you'd probably not recognise the original code. But fortunately, we can instead use the system.thread unit, and there is a T-parallel 4. So as you can see, there's quite a few overloads for it. We are only going to use one of those, and okay, we don't need. You can remove the end. For is a reserved word. Oops. So the first parameter is the stride length. I'm just going to set that to 1 for now, and we'll come back to it. Then is our low bound, 0, and then our high bound. And then it takes an anonymous procedure. Which has a single parameter of some sort of integer type. And so we no longer need our y. But what we do need is to shift x to be a local variable of our procedure. Otherwise it doesn't like it, because we would have a local variable which is being shared between lots of threads, at which point chaos ensues. So you can still shoot yourself in the foot, but it's a lot less difficult. So that's, I think, if I've written that correctly, that is we've now made our calculation multi-threaded. So if we now, fingers crossed, have done everything correctly. Calculate. So we're now sort of under 300 milliseconds to calculate. Now we can actually improve on this even further. Now the stride length. So the parallel for breaks the for loop up into chunks. And by saying 1, we're breaking it up so that each iteration is done in a new thread or a separate thread. Or I've got a Core i5 in this laptop, which effectively is 4 logical cores, two physical cores, which are hyper-threaded, which gives a total of 4 logical cores. So I can run 4 threads and do these calculations. So it gets split up, and so the first 4 get a single value for y to calculate. If I increase this to 10, this procedure gets called from a single thread 10 times, rather than essentially a thread, or getting a thread from the thread pool, and then calling the function once, and then calling the function, finishing that thread and then starting again. So instead we're doing it 10 times. Did that make sense? That was really badly explained, I think. So it actually doesn't make a huge amount of difference. So we're down to 220 milliseconds, thereabouts. Now you might say, okay, 10 was great, 100 is going to be better, right? So I'll set it to 100. So now each time each thread gets allocated 100 values to process. So the fractal is 480 pixels high. So we're now back to around 300 and something milliseconds. So what's happening is, so the first 100 pixels gets allocated to the first thread, and then the second 100, and then the third 100, and the fourth 100, and then there are 80 pixels gets left at the end. And so those four threads will eventually finish, and then one lucky thread will get the remaining 80 pixels to calculate, which is not parallelized at all. So there's probably there's probably like 17 or something like that, or some magical value that will be optimized for my machine, but it's it'll change depending on the size of the fractal we calculate, how many cores we've got, and all sorts of variables. So I'm just going to leave it at 10. Now, so that's pretty much all I've got in terms of the optimization. Yes?
Can you just discuss the fact that those threads are accessing the same data array and what the impact of that
Yes.
is?
Okay, so actually we're getting worse later on, but so basically the array is being accessed simultaneously by multiple threads, but it's an array of arrays, and it's really only an issue if 2 threads are accessing the same pixel, which is not going to happen because we're just racking over every pixel. There might be some clever optimizations we can do by making sure that the way it's calculated, the bits of memory are close together so they fit in the cache, they preloaded in the cache and all sorts of stuff. But
that's always the problem with like the VCL.
Yes.
You can't touch the VCL.
Yeah, we're going to have that issue very shortly. So down the bottom right, I'm going to throw a T animation indicator, and I'm going to set it to active, enable is true, and I'm just going to anchor it to the bottom right while I remember. And if we run this, okay, so it's updating our user interface, but when I start zooming in, it pauses. So and now that I've made it all optimized, it's going to be more difficult. So if I zoom in enough so that it's taking, try and shift the tunnel bar or something like that, the whole UI is freezing, which is one of those things you don't need to do. You need to keep your user interface responsive and interactive with the user and all that kind of thing. So what we want to do now is, so we calculate, we've maximized our performance in terms of calculating in background threads and optimize the inlining and constant parameters and stuff like that. We now want to improve the user experience. And to do that, we want to check the calculation of the fractal out of the UI thread. So we're basically going to create a background task, which is going to calculate the fractal, and our user interface will remain responsive. So to do that, we are going to again use the system threading unit. And we're going to look at this calculate and draw function. So we're going to use the task.run, which is basically just going to create a new thread and run in the background. We could actually just do create a new thread anonymous method, but we'll do it this way. And it requires an anonymous method. Oops. Okay, that's nicely lined up. So basically now this code is being run in a background thread. Does anyone want to point out the blatantly obvious problem?
You're accessing BCL.
Yes, from outside the main thread. Okay, so that's fairly easy to solve. tthread.synchronize. And again, oops, no. We'll write another anonymous. Oops.
Green.
Again. Another anonymous method, and there we have our thing being updated, our user interface being updated in the background. Oh, sorry, the foreground, where the calculations being done in the background. And oops. Ah, okay. You need to pass in a parameter there. Current thread or nil, I think is quite safe. And now, when we are calculating, our little indicator is quite happily still going round and round in circles. There's now another interesting problem which is created, which we will solve shortly. But first, because our user interface is now free to do something else, we could actually have it draw the fractal as it's being calculated, which is what we'll do now. So I'm just going to add a t-timer. And set this to, I think 20 milliseconds is okay. 50 times a second is quite quick. We could probably quite do 5 times a second or 10 times a second or something like that, but we'll go 20 and just call draw fractal. Now I'm going to not have this enabled by default. And so give it activate function. So window enabled. Undo it and save it. And this is not going to work because we set it true, not call it. Okay, and the other thing we could do is and we just hide it by default as well. So set it to visibility to false. so now it's been drawn. And you can see how it's sort of this kind of blinds effect. So it's doing these blocks of 10 pixels, which is our stride length. There's now, so I mentioned a problem earlier. Does anyone want to tell me what my current bug is? So I can...
Not clear.
No, okay, so the issue is I can click really quickly on the screen and it's going to say, calculate fractal the background, calculate the background, calculate the background. And so I end up with all these threads, all competing with, to draw their version of the fractal. And you're going to end up with something a bit bizarre at the end of it. So basically what we want to do, and kind of going to do this in a bad way, but is we want to cancel our current fractal that's being drawn when the user clicks and we restart a fresh calculation. So my lazy way of doing this is I'm going to add 2 new fields, cancelled, and oops, completed. I'm going to write the cancel procedure. So anyone who's done a lot of monitored programming is probably going to complain at me doing that, but anyway. Oops, this. So let's go back to our calculate. So we're not completed. We're not cancelled. And once we're done, completed becomes true. And from there. And there are lots of reasons this is why this is bad, but it works. So if exit. So basically, we're just terminating our calculation. The procedure will still get called, but it'll terminate really quickly. One more thing I need to do is set completed to true. Okay, so I think I've done that. So basically, we're just doing a busy wait, or kind of not very busy, but so we just set cancel true, and then we wait until the calculate method is finished calculating. Probably don't want to call cancelled. Yeah, no, it's all right. Yeah. So the reason I set the cancelled true, completed true in the constructor is that the first time we call it, it will call set cancel true and then wait for completed to be checked, but the fractal is not calculating, so just wait forever. And so we can come back here and say cancel. And I think there are actually still some timing issues involved in this, but I think this can be called, this cancel can be called, and the calculate can finish, and I think the timer can get not enabled or something like that, but it works reasonably well. So it basically means we can now click quickly and so we're going to have to wait till the entire fractal has finished drawing before we zoom in. And we can probably reach our maximum number of iterations pretty quickly. So this is the next thing I'll so it's not really important to the talk, but as I zoom in, notice how these were nice round circles previously, and they're kind of now sort of bleeding out. This is basically, we've reached our maximum number of iterations. So the colour closest to the black is our sort of 1024 iterations. And it's now taking more iterations to sort of get the defined edges. So what I'll briefly do, just to, what I normally do is have a little edit box in here we can texture on. What we'll do, with the compiler here, if we come into calculate, what we can do is just set the maximum iterations to any value. So it's currently 1024. We'll quadruple it and carry on running. And we've now got, you can see it being drawn back to the nice circles. The downside of having a higher number of maximum iterations is the black area always reaches the maximum iterations. So the more black you've got, the slower the calculation. And again, we're kind of reaching the sort of maximum iterations sort of really quickly by zooming in towards the edges. Okay, so questions? Yes?
Is there one redone the algorithm as a logarithm so you don't have the floating point issue?
Sorry, the old.
Do the algorithm using logarithmic techniques so you don't have to use the floating points and sideways and stuff?
Not that I'm aware of. I mean, I've done fractals using integers.
Well, I've never. I've looked at the books. That's my understanding.
Yeah, so you can approximate floating point numbers with integers and doing sort of shift left, shift right type operations. But you don't get to zoom very far. If
you use a logarithm, in theory you could have a fairly long log, which is the normal way of using them, and then an integer that's 16 bits, and in theory the floating point problem should go away.
Okay, I don't know. I'm not familiar with the mathematics for it. So.
Yeah.
Okay, so we've got our Windows version. I wrote it on FireMonkey. So in theory, we should be able to compile. And let's have a look. See if it's on my phone. Yes, it has. Connection.
Just in relation to Andrew's question, the logarithm's going to work because there's an add in that expression.
It should make it more difficult, yeah, because logs will slow it down, like doing a multiply.
Yeah, but if you're doing the logs, then you lose the ability to add the C.
Yeah.
Okay, I'll just run that with debugging.
It's weird, because,
So that's my Android phone. It's a LG G4, I think. Yes. And so it is busy building our app and then compiling it, and it's called Project 1. I wonder if I've already got Project 1 on here. If I had only to install it before. No. So this is one of the wonderful reasons Delphi is great, because you can test your application in Windows, and you don't have to go through this painful deployment stuff to Android every time you want to confirm that it's still functioning. Okay, here's our fractal. It's a bit stretched. But we can do the same things. Let's just tap with my finger. as we do more calculation on the phone, the latency of the update gets a bit worse. But the phone has 6 cores in it. There are 2 sort of, I think, that are running at 2 gigahertz, and then 4 that are running slightly slower. All 4 of them can work at once. I should have something telling us how many cores it's able to take advantage of. And if I click somewhere, click with a mouse somewhere up here, it's probably going to be completely the wrong spot because I've not handled. I did actually modify it so it didn't crash while when rotating, so that's probably a little bit of a bonus from one of my previous versions. So there was one other topic I wanted to cover today, but I'm not going to be able to because it's turned out to be quite difficult. So we've got it running on my phone. If I wanted to do the user interface on the phone and do the sort of exploration and what have you on the phone, but my laptop is way faster than my phone for calculation. So it would be quite nice to be able to have, tap on the phone, but do a number crunching on the laptop. So I had a go at this using app tethering. It proved to be a little bit more tricky than I expected. So I'm not really going to be demonstrating that aspect of it, but I've got, if I close this one.
Was that due to app tethering issues, or was it just
No, app tethering was okay. It was just that you're being on the code.
Okay.
And app tethering seems to be a little bit quirky as well. So I found it's way better than writing yourself. But I came across some interesting issues. So basically, I've got this version, which we've got a tethering manager and profile, and we go connect. It does auto connect. Interestingly, it connects to one of the features I haven't actually tried out yet is the ability to preview the screens on your phone and devices. I think that uses app tethering, and so it picks up and connects to that for some reason. With the auto connect, probably shouldn't, but anyway, so you've got to bear that in mind when you're wondering why am I getting this extra connection testing. But anyway, so I have this calculate on remote, which presently it just goes through and finds a remote. Too long? 5 minutes? 10 minutes? Okay. Finds a remote profile with the in the same group, and then just sends a string calculate, and I created this Mendel param, so basically converts all those parameters, the top left-hand corner and the maximum iterations, all that kind of stuff, into a string, and passes that, and it sends that string, calculate string, and also includes the local identifier. One of the odd things I've noticed about app tethering, and there might be some way of discovering it, is that when you receive a message or a resource, so when you receive a resource, there doesn't seem to be a way of telling who sent you that message, which seems kind of strange, but you basically just include the identifier. So basically, I'm just grabbing the identifier profile ID as part of the message. So basically, I calculate, create a new fractal, set its parameters, calculate it, and then I create a memory stream, and then iterate over that the array and shove all those integers into that stream, and then I need to send that back to the person who sent me this request to calculate the fractal, and I use the send stream function. and then, so it sends a stream and says it's a fractal. And so when we receive a message that is of type fractal, we then read from that stream all the integers and plug them back in. So it's not hugely horrible. It's pretty much what you end up. It's basically what you end up writing if you were to do it manually using NP or something like that. But this is somewhat friendlier. There's also some issues in that all the connections are established via UDP, and then the streaming is done by TCP. So UDP is not efficient for streaming large amounts of data, which means you're creating these TCP connections, and all that sort of stuff is quite expensive, and so you end up losing a lot of your performance gain. But if you wanted to do like that Mendel animation at the beginning, if you wanted to calculate something like that and wanted to frame out, if you had a whole bunch of machines that you could say, you calculate this frame, and so on, and then get it all back together, that would probably be a reasonably efficient way of doing it. And I might see if I end up writing that, because that'd be quite cool, to have a fractal farm. Any questions?
What about using the data from one point to work out the next, like you do real video?
Sorry, well, so another...
Just looking at it as an algorithm, like,
so
it's been a year since I've done HDTD stuff, but you cross the line, you go, oh, okay, all those pixels.
Yeah, so there's cheats. Yeah, there's definitely cheats you can make. If you remember, anyone remember Fractant? It was an old application that ran on 386 and it calculated fractals. It had a bunch of optimizations. No, components for Android again. Let's go back to our original and I guess 64 Windows. Sure. So first off, there's top-bottom symmetry. So this pixel is going to be the same as this pixel. So that's not an optimization we could make. Take advantage of the fact that it's a mirror image. And the other thing is, yeah, there's these large areas which are the same color. So you could kind of do it statistically and say, well, if I do kind of a bunch of probes, that whole area probably is one color, so I'll just color it one color. And so Fractal did some clever things like that. And there's also mechanisms of kind of finding the edge and then calculating around the edge, rather than calculating per pixel and then sort of filling in the gaps. Yeah, they're quite complicated algorithms. So yeah, anything else? Okay, lunchtime, I guess.